All right, we're back in action.
Good afternoon, Sharon.
Good afternoon, Diane.
And so it's a nice day today. The sun is shining.
Very windy, though.
I say this
windy.
presentation is being brought to us by the sun.
Very nice. Yes, the sun. But my spicy green olives did come, so we could say that it's brought to us by Tabasco and the Scoville unit as well, if we would like to. So.
Wow. Well, we are certainly creative today, aren't we? So
Yes.
Today we are going to launch into biomechanics, and in this class we really just kind of hit the introductory levels of biomechanics, but we're going to start our discussion today by talking about levers.
Yes, if you guys are fascinated by biomechanics, then you can actually go to graduate school and get a degree in biomechanics. Certainly Sharon Brattrud did not go and do that.
I didn't either, but I'm going to guess Shelby might be interested because
Shelby
you have
might.
to be
There's-
really good at math,
yes,
Shelby.
There's a lot of math involved in the biomechanics, how our bodies are moving, and so if that does interest you, then there are certainly other avenues if you would like to take this subject further than what we are presenting.
So we're going to start by talking about levers, and I just want to reiterate what the textbook does tell us, that a lever is a rigid bar that turns about an axis of rotation. And so it's a simple machine, basically. And when we talk about something rotating on an axis of rotation on a lever, we refer to that point as the fulcrum. That's the axis of motion. So all the motion occurs at that fulcrum. Now, Sharon, what would be an example of a fulcrum in the human body? An axis.
A fulcrum in the human body would be when we plant our flex, we do a toe up, okay? Then the fulcrum would be at your ankle.
See, and I was looking for a more simplistic answer and say an articulation.
Oh, I see. Okay. Sorry, I was getting too involved in the biomechanics.
She's right to biomechanics major that she always wanted.
Right.
So when we talk about the axis, this axis rotates, and it's going to be based upon the force that is applied to it to cause the movement, and that movement always happens against a resistance. And so that resistance is a load or a weight. So we look at the three parts of the lever, and we see that we have the fulcrum that we already talked about. That's where we're going to get the rotation. We have a resistance point, and that is the exact point where the resistance is going to act. And then we have a force point, where is the exact point where the effort is applied. So now if we take this to muscles, the force point could be defined as the insertion of a muscle. Unless that muscle is functioning by functional reversibility, then it might be the origin. So we have three different classes of levers, and how we arrange these three parts determines the class of that lever. So here on this slide, we're seeing the three classes of levers.
Can you see me writing, by the way, when I write?
Yes,
Watch next.
I can see
Okay.
Sharon writing. So in the previous slide, we talked about that the levers are defined by, or the levers, if we'll speak some Drew language here, in the Canadian professors will call this a lever, by the way, but the levers are defined by the arrangement of the three parts. So let's look at the first class lever. In the first class lever, the fulcrum is located between the resistance and the force. Now notice I said between. I did not say in the middle. And you'll notice in this first class lever that fulcrum, which is identified by the orange triangle, is not in the exact middle. It's just between the two. You'll also notice that the resistance and the force are not equidistant away from the fulcrum. The R and the F are placed there intentionally. And you can see in this example, the force is closer to the axis of rotation than is the resistance. So when we talk about a first class lever, many times we'll define this lever as a lever of balance or a lever of range of motion. So if Sharon, what would be a great example of a first class lever out in just in the world in general?
First class lever would be like a seesaw, teeter-totter.
Great answer, Sharon. You can all see this now, right? It's a
I had
teeter-totter.
to think for a minute. Don't put me on the spot like that, Diane.
Okay, a second class lever is where we see the fulcrum at one point, one end, the force is at one end, and the resistance is in between. So the load or the weight is between the rotation point and the force that's being applied. This lever is defined as a lever of a mechanical advantage. And what that tells us is that we can do a lot of work with less effort. I'm going to put Sharon on the spot again. Can you think of an example of a second class lever?
Is that going to be like a wheelbarrow?
Yes, a wheelbarrow.
Yep.
And
Can I ask before you move on,
Yeah.
what is the C in the, what does that mean in this second?
I think that means that
That-
Diane made a mistake.
Oh, okay. I just want clarification for when
Yes.
you guys are studying that I think the C probably doesn't mean anything, so we can disregard that
Yeah,
C in the
disregard the
triangle in the
C.
fulcrum.
And then we have the third class lever. And in a third class lever, once again, like a second class lever, the fulcrum is at one end, but now the resistance is at the other end or towards the other end, and the force is in between the two. So if we think about the human body now, this is kind of what the human body looks like. If we think about the forearm, and let's think about elbow flexion. We know that the biceps brachii muscle inserts on the radial tuberosity, correct, of the radius?
Yep.
Okay. And if I was going to lift something, I would have that weight in my hand. So the load would be in my hand. The force would be at the insertion point. And so as we flex the elbow, that is a great example of a third class lever.
And where's the fulcrum then? It's at the
The
joint.
elbow, yes,
Right.
it's at the axis of
Just
rotation.
so we know exactly where they are.
So if we think about these, and a third class lever, by the way, is defined as a lever of speed. Third class lever, a lever of speed. Now you have to think about how the human body is configured. Certainly, we don't do a lot of things slow in the human body. If we're going to lift a bunch of weight, think about a clean and jerk. That clean of that weightlifting exercise is done with speed. So, we use the elbow as an example, and most of the joints in the human body are going to be classed as a third class lever. Second class levers, sometimes we'll look at, Sharon used that example before, raising to the, on your toes from the ball of your feet. The ball of the foot is the axis, right? The force applied is at the calcaneus, and the resistance of the body, the weight actually shifts to the toes as we lift up. A first class lever, typically we look at the triceps in shoulder extension, triceps and shoulder extension, working as that first class lever. So 3 classes of levers. First class lever, we think about balance, always think about teeter-totter and range of motion. Second class lever, we think about mechanical advantage. We don't have a lot of them in the human body. We can use that example about doing that kind of toe raise. The jaw, we don't talk about those muscles, but the jaw can work as a second class lever. And we think about mechanical advantages, a lot of force applied. Third class lever of speed, most instances in the human body. So we've talked about this I have a question. So what is the point of rotation called in a lever? Think about this. I'm not looking for the word joint here. I'm actually looking for the technical term. So we're going to move on here to the next slide. And this is where we talk about mechanical factors. And so when we talk about levers, we have 3 mechanical factors, and we've talked about them already. We have force, we have speed, we have range of motion / balance. And we don't really look at balance as being a mechanical factor, so we think more of range of motion there. If we reduce any one of those, we're going to get a gain in one or both of the others. So if we reduce speed, we're going to get a gain in force and or range of motion. If we reduce force, we're going to get a gain in speed and or range of motion. So that is how those three mechanical factors will either reduce or they'll gain within the human body. Now we're going to maybe have a question. I'm not sure. Nope. We're going to do a little activity. We're going to put Sharon on the spot.
Uh-oh.
So we're going to look at these levers that we have here. And I misspoke earlier. I want to say triceps at the elbow is the first class lever, not at the shoulder. I'm sorry.
Okay.
Yeah. So let's look at A. Sharon, first, second, third class lever.
First.
A?
I don't know. Oh, I was looking at B. I
Okay.
apologize.
Really?
Sorry. A, hold on. Because it's hard for these eyeballs to see.
Resistance is in between.
That would be the second class.
Exactly. Good job. So what do we have that looks like a second class lever out in the real world? A nutcracker. A nutcracker works just by that premise of a second class lever. And if you've ever tried to crack a walnut with just your hands, it can't be done. But you put that in a nutcracker and you get that job done really well. So now with a nutcracker, you gain force.
Yeah.
B, she answered that earlier. What is B?
Did I say first?
First class lever. Here we go back to that tricep, how it inserts on the olecranon, right? So the olecranon is a process outside of the joint a little bit. And then we see the axis of rotation is just slightly displaced towards the distal end of the forearm. And the weight is at the end, or the load is at the end. How about C? I know you're going to get this one.
C is teeter-totter.
Yeah, so that's a
First class.
first class lever again. And notice how, once again, we're not putting the fulcrum in the middle. We're putting the fulcrum just in between. And so here we see that force is going to be the advantage here, isn't it? We're going to get into force arms and resistance arms in a little bit, but we're going to be able to apply a lot of force here. And then finally, D would be
D
our
will be a third class.
lever, because we have our fulcrum, resistance towards another end, and then we have that force in the middle.
Can I ask one question?
Yeah.
On B?
Yeah.
The fulcrum is between the two. Mm-hmm. That's not a first. Or that, you
No,
know.
it is a first.
Yep. Sorry, my bad.
That's okay. We're going to let you go with that one. You're absolutely right. The fulcrum is between those two.
Whoopsie. Yeah, see, I have to study myself.
Now you know how I feel sometimes.
Yeah.
Now, here is, we've talked about first, second, third class levers, but the elbow is really interesting because we can actually apply all three levers to movement at the elbow. So the first thing we always have to define, we've talked a lot about where the resistance is, but resistance has a point. And so if you're holding something in your hand, like a 25-pound weight, that resistance point would be in the hand. But if we have a limb with no external weight applied, that resistance point is 3/7 of the distance from the proximal end. So in the case of the elbow, that would be the elbow joint, that would be the elbow joint, when no external weights are applied. So if we look at the three levers here of the elbow joint, we've already talked about one, first class lever, that's tricep in elbow extension. We've already talked about third class lever, that is bicep, the biceps inflection. And then we have this kind of odd one, and that's going to be the brachioradialis. That's going to actually be a second class lever. And, you know, as we talked about before when we did, brachioradialis is not a terribly significant muscle, I wouldn't say, but it does give us a lot of force in twisting motions. And so we get kind of mechanical advantage in that case. So let's look at how adding an external weight can cause a lever to change its class. So here we have two examples, and the hands are empty in the first example. So if the resistance, and this would be an example of the brachioradialis, actually, if the resistance is 3/7 of the distance from the proximal end to the distal end, Sharon can mark that resistance point, resistance point, which would be almost in the middle of that bottom bar.
Toward the hand or
Toward, just a little bit closer to the elbow than the middle.
Okay.
Yeah. Did you mark that? Now it doesn't show up, but hopefully this will show up later.
It's a small mark, but.
Okay. And we know that then the force point is the insertion of the muscle, which is then out towards the round ball, signifying the hand. And we know, of course, that the fulcrum is the joint, the articulation. So in this case, we go fulcrum, resistance, force. So that organization, fulcrum, resistance, force, will give us a second-class lever. But now what happens when we add an external weight? So let's say that, well, maybe a 50-pound dumbbell might be a little crazy, but let's just say we add any weight to the hand. That now, the fulcrum is still in the same spot. But remember, we said that the resistance point is 3/7 of the distance from the proximal joint to the distal of the limb, if no external weight is applied. But now we have, in this case, a huge amount of external weight. We have 50 pounds. Now our resistance point goes all the way out to the hand. So now our arrangement of this is fulcrum, force is going to be before the resistance, Sharon, because the resistance is going to be out on the weight. So we have fulcrum, force, resistance. And now we have
Can't write on this very well.
third class lever. It's starting to show up now, though, online.
Yeah, let me try this again.
Okay, and as Sharon's doing that, I want to just go back to that first bullet, because I'm using a term here that we're going to talk about on Thursday, COG, center of gravity. When we talk about how adding that external weight can cause a shift in the location of the center of gravity. Center of gravity can also just be, think about the center of weight. Center of weight. And so certainly the location or the focal point of our weight in this second example goes out to the hand. Well, she is writing with some good penmanship today.
Not really.
So, the mechanical advantage of a lever is equal to the ratio of force. So it can be expressed as load over effort or effort arm over load arm. And I want to talk a little bit about the effort arm and the load arm here. And what I want is, Sharon, just to draw a first-class lever on this diagram, which would be fulcrum in the middle, resistance on one end, force at the other end. Or in between, not in the middle. We have a little delay in how
okay?
this is, it's a little delayed. It's not showing on my screen yet, so it wouldn't be showing the student screens yet. When we define a load arm, we want to also call the load arm the resistance arm. And so the resistance arm is the distance from the fulcrum, resistance or load arm, same, we can interchange those, the distance from the fulcrum to the resistance. So wherever that center of weight is or the center of gravity is.
Load arm.
That's the load arm.
Now you don't want to write.
And the effort arm, we can also call the force arm. That is the direction from the fulcrum to where the force is applied. We're using a simple first-class lever here, but if we thought about a third class lever, that force arm would be from the joint to the insertion of the muscle.
What do we want to call that?
That is the force arm or the effort arm.
Okay.
Because on Thursday we're going to be doing some application with some math.
Doesn't want to write. Sorry guys, it doesn't want to cooperate, but it's kind of how it goes with us, right? Oh, good Lord. Okay, let's try it again. Okay, oops, we took off there.
So load arm would also equal resistance arm, RA, and effort arm would also equal force arm, FA. And I think what we'll see is a lot of the formulas will use the RA and FA.
Hold on, repeat that for me.
The load arm is the resistance arm, RA,
RA, yep.
RA, and the effort arm is the force arm, FA. So now we're going to show a little video here. Oh boy. Let's see if Diane can make it work.
Doesn't want to do it.
This might help clear some stuff up, I hope, for us. Maybe.
You know, I've always wanted to do about 3 things with my life. Call it a bucket list, if you will. First, I've always wanted to hug a tropical plant. Done. 2, I want to hang out with David Bowie. Not done. And 3, I've always wanted to teach people about mechanical advantage. Let's roll. Welcome. Mechanical advantage, welcome. So let's say we got a lever, this little machine. The purpose of the machine is to make our lives easier. That gives us a mechanical advantage, or a ratio of force. Now, the first type of force that we need, right, is the size of the load, which usually is the weight, gravity times mass, okay? And then we have the size of the effort. It's our work that we put into that lever, okay? So the mechanical advantage formula is the force of the load over the force of the effort. So let's run through a little example. Let's say you have a 1988 Dodge Aries K car, which by the way was my first car and I still love it. It's stuck in the mud though, can't move. So we find a rock, a giant log, and we decide to make a first class lever. And we put an effort there to lift up the load. Now, the force of the load and the force of the effort are 2 different things. Let's just say that this load, this Aries K car, 2,500 newtons of weight. And this machine only requires 500 newtons of effort. So let's put it into our formula. Force of the load, 2,500 newtons. Force of the effort, 500 newtons. When we divide this up, we will have this ratio of force. So you'll notice that there is no units. That's what a ratio is. Oh, sorry about that crappy A. The mechanical advantage, this is the important stuff. When it is greater than 1, you will have a multiplication of your effort. It means that this machine, look at this glorious machine. Look at it, it's right here. Oh, it means that it will make your effort 5 times more awesome in order to lift up the car. You couldn't put 500 newtons with your bare hands and lift it up. However, if the mechanical advantage is less than 1, then you have a speed effect. Now that's good. It'll do the job faster, but it'll require a lot more force. Okay, this next little section can be a little bit difficult because I'm going to attempt to help you understand that the mechanical advantage in terms of newtons, right here, in terms of force, is directly proportionate to distance. Check this out. You have this first-class lever, there's a big fella, and there's a little fella, okay? You have your little fulcrum there. This big guy is exactly 3 times as heavy as this other little guy. So we have ourselves a ratio right there. But we know that if we move the fulcrum this way and that, it changes. One is more difficult, but it'll get the job done fast. and one is really easy, but it won't lift as high. So this is the mechanical advantage we were talking about in the previous example. So we have our effort and our load. The effort obviously is the big guy. So we have the load, little guy, 1 part, and big guy, 3 parts, okay, in terms of force. But this also equals or is proportionate to the distance or the effort arm, okay, over the load arm. Now the effort arm, okay, when we have this, here, let me redraw this. Here's our effort, here's our load. The distance between the effort and the fulcrum is the effort arm. The distance between the load and the fulcrum is called the load arm. So when we move that fulcrum from side to side, it changes our mechanical advantage. So the question we can ask ourselves now is, how far would we have to move the fulcrum closer to the effort so that it's exactly flat? If we've got a big guy that's 3 times as heavy as this one guy. So we look at all this. Here's distance in newtons. So let me just redraw our little plank, because we have, in proportion, 1 part load, 3 parts effort, okay, for the force, which is directly proportional to 1 part effort arm to 3 parts load arm, okay? So the distance is the same proportion as the force, where 1 part is effort and 3 parts load.
So that gives us kind of a little synopsis of how we can compute this ratio. We can do it by using distance, which uses the arm, and Sharon diagrammed that for us, and we saw it again in the video, or we can simply do it by using weight and force. So just always remember that it's a ratio. So in very easy terms, we have an example here. If you have a wheelbarrow and you put 200 pounds of dirt in it, but you only can apply, and with only 50 pounds of effort, then you have a mechanical advantage of 4. 200 divided by 50 equals 4. That is why a second-class lever is such an advantage to us, because we get this ability to do more work. So, we have a question. Where is the resistance point identified on human limbs when no external weight is applied? And we talked about that. So look back in your notes and let's find the answer to that, because we're going to be using that on Thursday. So movements occur when levers are unbalanced, and that's what that video showed us, that we have to balance them by manipulating the arms of load and the arms of effort, or the arms of resistance and the arms of force, because we can use those terms interchangeably. That we get movement when we create unbalance. And so what we use to compute a lot of our math formulas or our math equations with concerning levers is we use a formula that we call the law of levers. So the lever will balance when the product, and the term product just means you're multiplying 2 factors, so that when the product of force is multiplied by the length of the force arm, and if that equals the resistance multiplied by the length of the resistance arm. So we have F times FA equals resistance times RA, or resistance arm. And we talked about load is R and effort is force, if we go back to that video. And we're going to come back to this formula on Thursday, because we talk about this is when it's balanced, but what happens when it's not balanced, when we unbalance it? So the question we have is, why are motor skill levers seldom balanced, Sharon?
Because they're not equal.
And why else? Probably because we want movement.
Oh, yes.
I mean, movement is desirable. So when we look at the human body, we are using third-class levers. We have very few first-class levers, because the desirability of what happens at the articulations or the joints is to give us movement. So we don't want that balance. And go back to when we talked about the factors that are benefited at those levers. The first class lever, we get that balance is one of the things that we can get from that. So essentially that formula almost illustrates a first class lever if you thought about the equal sign being the fulcrum.
Yes.
So Sharon, do you have any questions? Anything we need to kind of key up today? You know, high points here. Most of the levers in the human body are going to be third class levers.
Yes. And I know this stuff is very confusing. It's confusing for me too. And just note that this is certainly an overview of biomechanics.
Yeah.
And I know that in the coming lectures, in the coming days, Diane is going to be reinforcing what we talk about in the previous lectures into the next lecture, especially since we're not face-to-face right now to answer questions and to help understand this a little bit more.
There is going to be a little knowledge check again that will be required at the end of the class period today, Tuesday. I'll put an announcement. There will be an announcement that you will have gotten.
And so I sent you out an announcement this morning saying that nothing was due for tomorrow. But after we watched this, then I apologize on that because I was unaware that we were going to have a knowledge check after the lecture today. So,
and if we have a few late ones, we have a few late ones on that one. And essentially the knowledge check that we're going to have after this is being able to identify the different classes of levers.
Yeah.
On Thursday, we're going to get a nice big story problem, and we're going to apply mathematics to levers so that we can determine specific resistance points. You know, how much force does a muscle have to apply to move a limb? Because that's the whole essence of levers in the human body.
yeah. And what I meant was nothing is due prior to class for tomorrow.
Right.
You'll watch you'll listen to the lecture and look at the PowerPoint. And then take your knowledge check, just like we always have. But nothing's due for tomorrow's class.
Now, the whole thing about biomechanics, this is not as black and white as a muscle originates here and a muscle inserts here, and these are the actions that it does.
Correct.
There's a lot more gray area. So if you have questions, please use that Cyber Cafe so that we can clean that up.
I think you have another slide.
I don't think so. No.
You have a question?
I have a question, though. I thought we were done. What mechanical factors undergo reductions or increases in the lever system? So what things do we manipulate? We listed 3 of those earlier. I didn't have another slide, but I did have a question.
I said,
So anyway, we'll come back and try to digest this information and draw pictures of those levers. If you're someplace where a playground is open, go look at a teeter-totter, get a nutcracker out, get a wheelbarrow out, look at those things and manipulate them, and that might just get these things to make a little bit more sense to us as we go through it.
Yep.
All right? So I'll talk to you all on Thursday, as will Sharon, and Sharon, I'll see you again sometime.
yes, you guys have a great day, okay?